Aloha, this is RBrewer with the Hawaii Department of Health. This is a recording of a presentation that I gave at the Battelle Conference in Palm Springs, California in May 2016, entitled Why Discrete Soil Samples Lie and Why Multi-Increment Sampling is Important, a Field Study of Heterogeneity. Now, a lot of people listening are probably familiar with our decision unit and multi-increment sampling site characterization guidance that Hawaii initiated over 10 years ago now. What I want to do today is step back for a moment and look at the origins of discrete soil sampling, especially explore the details of what exactly the problems are with discrete sample data. This is a great quote by Morpheus from The Matrix, if you haven't seen that movie. But we knew for decades that something was wrong with the way we were collecting samples and with the discrete soil sample data that we had. But we really couldn't figure out what the specific problems were until we started exploring these decision unit multi-increment sampling methods and looking more deeply into sampling theory. So let's step back first and look at the origin of discrete soil sampling. Why, now that we know we have so many problems with this sampling method, why did we get started in the first place? One thing to point out too is the reliability of discrete soil sampling methods was never tested in the field at the time some of the original guidance was being prepared. Here's a great quote from EPA 1985 guidance on the verification of PCB spill cleanups. It's the implicit assumption that contamination is likely to be uniformly present anywhere within the sampling area is reasonable. So here they were assuming that contamination in soil would be very uniform. This relates to the expertise that the people writing the guidance had in studying wastewater discharges, where the concentration of contaminated in wastewater from an industrial facility was fairly consistent. It didn't really matter where you collected the sample or when you collected, as long as they didn't change the process in the facility. This was followed up in 1989 US EPA guidance methods for evaluating the attainment of cleanup standards. When there is little distance between points, here they're talking about soil samples, it is expected that there will be little variability between points. Well, as Dr. Phil might say, how's that working for you? And again, we've known since the late 80s, early 90s that this wasn't working out the way we thought. Very common things you see in the field are a need for multiple remobilizations and step-out investigations to collect more and more discrete samples, really with no end in sight. And this has caused some site investigations to drag out for years. Another common problem expressed in the field is failed confirmation samples and multiple over-excavations after you've collected confirmation samples around the edge of where you thought the contamination was, carried out the excavation, collect additional samples, and find out there's still contamination there. Another problem that we deal with quite often here in Hawaii is accidental import or export of contaminated soil, where again you have a small number of discrete soil samples to characterize the soil, indicated there wasn't any contamination of significance, but then later testing of the soil and more thorough testing has demonstrated that there is indeed a problem. So what's the problem? I think anyone who's ever worked in the field has thought of these two questions. What if I move my discrete sample point over a few feet? Would I get the same number? Or at the laboratory, what if the lab tested a different aliquot or subsample of soil in the sample I sent in? One thing important to understand with labs, when a lab tests a soil sample for metals, typically only testing half to 1 gram of soil, or about a pinch. When they test soil for VOCs, they're only testing about 5 grams of soil. This would fit into a bottle cap. Testing for PCBs, pesticides, pHs, dioxins, other chemicals, laboratory typically tests 10 to 30 grams, or roughly a spoonful. So these are really small masses of soil. Now, discrete soil samples are rarely processed properly in the lab. I'd say never processed properly. You often hear that the sample was homogenized at the laboratory, but this can be very misleading. A lot of times, attempts to homogenize a sample in a jar of soil will actually make it worse, where a fine material will settle to the bottom of the jar, and the coarser material will come up to the top of the jar, and the fine material could be where most of the contaminants are to begin with. So in the end, data are only really reliable for the mass of soil actually tested. Well, we had these questions too. So we went out in 2014, 2015. We carried out a very detailed field study of discrete sample variability. We picked 3 sites with known contamination. Each site we designated 24 grid points And then we collected hundreds of discrete samples at each of the sites and tested all of them and evaluated the variability between the data. The 3 sites we selected, study site A was a site known to be contaminated by arsenic in wastewater and very fine-grained soils. We already had data at this site suggesting heterogeneity was fairly low, especially in comparison to other sites. Study site B was a site contaminated by lead from incinerator ash that had been mixed with fill material and spread out around the incinerator itself. Study site C was a site contaminated with PCBs from transformer oil, electrical equipment that had been dumped on the ground over the years. And we had data for the PCB site also that indicated very high heterogeneity and variability around individual discrete sample points. And we assumed that the lead site would probably be somewhere in between the arsenic site and the PCB site. Here's some references for the study. The field reports small-scale variability of discrete soil sample data dated June 2015, posted to our web page. Part 1 just presents the data. It's a field investigation of the discrete sample variability. Part 2 looks at the causes of this variability and the implications for use in environmental investigations. We're also preparing a manuscript for the study, and we've submitted it to a journal and hope to have it published sometime later this year. So here's what we did at each site, and at each one of the grid points designated each one of these sites. The first thing we looked at was what we refer to as intra-sample variability. The basic question is, are laboratory data representative of the sample submitted? So what we did for the lead and the arsenic site is a single sample was tested 10 times using a portable XRF in a laboratory controlled environment. So we could look at the variability of lead or arsenic concentrations within a single sample. The PCB site, we took a single sample and split it into 10 separate small jars and had the laboratory analyze the soil in each one of those jars. And we could look at the variability of PCB concentrations within a single sample. Next thing we did was look at inter-sample variability. And in this case, the basic question is the sample representative of the area where it was collected? So what we did to investigate this question is we collected 5 co-located discrete soil samples around each of the grid points. Each of these samples was IS or MIS processed at the laboratory for testing to make sure we got representative data for each of the samples. So they were dried, sieved, and subsampled in accordance with multi-increment or incremental sampling processes. In this case, for the metals, we used method 6810B. It's an extraction method by the laboratory. And you'll see later on there's some difference between the concentrations of metals reported for samples using an extraction method versus an XRF method. I'm not going to go into detail in that other than to say for example, the arsenic concentrations reported using the XRF were much higher than the extraction method because of poor extraction. That didn't really affect the overall results of the data and conclusions. So again, these samples were processed and the data are assumed representative of that sample. So here's the results. This is the arsenic study site where again we expected lower variability. Indeed, that's what we saw. This is a grid point 2 example of data looking at intra-sample variability. The lowest concentration of arsenic reported for the sample was 141 milligrams per kilogram. Highest concentration of arsenic reported in the sample, again using the XRF, 204 milligrams per kilogram. Now the average maximum to minimum ratio of arsenic in the samples was about 1.5, so not that different. The maximum to minimum ratio we saw for arsenic in any given sample is a little bit over 2.5 times between the maximum and minimum. So that's the variability within samples. Let's look at variability. So this is the data for co-located samples at the same grid point. So the lowest concentration of arsenic reported in the samples, 120 milligrams per kilogram. Highest concentration, just a foot or so away, 260 milligrams per kilogram. Again, these don't represent large-scale trends in arsenic concentrations across the site. They're completely random. Still very similar to the variability that we saw within individual samples. The average maximum minimum ratio at around the grid points for co-located samples around 1.4. The maximum maximum minimum ratio we saw in co-located samples around grid points, just over twofold. So overall fairly low, although this could obviously cause some concerns if you're using discrete sample data to measure the extent of contamination. One thing I want to point out here, we saw this at each of the sites, but the variability between co-located samples and even within samples, it's not a function of the concentration of the contaminant in those samples. We saw very similar variability in samples with very high concentrations of contaminants as well as low concentrations of contaminants. So next, let's look at study site B. It was contaminated with lead. And again, we anticipate to see more moderate or higher variability at this site, and indeed that's what we found. And this is where the fill material was contaminated with ash from the incinerator. In this example from grid point 7, again looking at intra-sample variability within a single sample, lowest concentration of lead reported using XRF was 166 milligrams per kilogram. Highest concentration of lead reported in this same sample was 337 milligrams per kilogram. I'd point out too that the XRF is testing around 1 gram of soil, which is very similar to what a laboratory would analyze. So here we did see a higher variability within a single sample. It's actually higher than this example. On average, maximum minimum ratio of lead concentration is about 4-fold. The maximum ratio of the maximum to minimum concentration of lead reported for any given sample was 15-fold, or over an order of magnitude difference. This site, just coincidentally, in essentially every grid point at the site, we found concentrations of lead in the soil that were both below and above our action level of 200 milligrams per kilogram. So start thinking of the implications of that. Okay, let's look at the inter-sample variability. Same grid point, lowest concentration of lead reported in the samples, 120 milligrams per kilogram, and then just 1 or 2 feet away, concentration of 800 milligrams per kilogram is reported in the sample. And again, these aren't representing any large-scale trends. This is totally random around the grid point. The average maximum minimum concentration reported for these co-located samples about 2-fold, so actually less than what we see at this particular grid point. Maximum to minimum ratio about 7-fold or difference between the maximum minimum concentration in lead in co-located samples. So definitely higher than the arsenic site. Let's move on. So think about the implications for this before we move on to the PCB site. So on the left is just a pie charts of individual grid points showing that the green demonstrates the individual samples that were below our action level. Red indicates individual tests, I should say, that were above our action level. So in this particular slide here, 18 of the 24 grid points, we identified lead concentrations in soil both above and below our action level. If you look in more detail, when you start combining the variability within samples and between samples, you would be able to find soil at each one of the grid points where the concentration of lead was below our action level and above our action level. So think about the implications of that. On the right, depending on which random set of discrete samples you collected at this site, every point could come up above our action level, or every point could come up below our action level, indicated in all red and all green in the upper right. More likely, you'll get a random pattern of points at the site where some points are below the action level, some points are above the action level. And a very strong characteristic of this type of random variability in soil is you'll start to see isolated hot spots and cold spots in your discrete sample data. And you also see apparent large-scale patterns of contamination. So in the bottom left-hand corner, the 4 small figures, it looks like most of the contamination might be concentrated over on the lower right-hand corner. If you were to go back and resample that same area, then you'd find similar patterns, but they could be completely switched, as you see in the bottom right-hand corner. So these are all artificial patterns. They don't represent what's actually happening at the site. They're just reflecting random small-scale variability. So keep that in mind. We'll look at that again later on when we actually look at site data. So which one of those patterns is real? Well, here's a hint. None of them are. This small site that we studied is actually part of a 10-acre site where it's covered with fill material. It's mixed in with lead-contaminated ash. So think about that. If you were attempting to use discrete soil samples at this site, to characterize it. The first area you tested, you would probably find lead contaminated soil, but as you started your step out investigation, very quickly you'd identify samples that were below the action level, and you'd think you'd found the extent of contamination. So you might do some excavation, collect some confirmation samples, find more contamination, and then do over excavation. So just think about the problems that would cause as you're trying to investigate a site and you're actually in the middle of a huge field of contamination. So that's a key point, is the estimation of lead concentration at any given discrete sample point. It's not meaningful or even feasible in terms of attempting to map out contamination at a site. Let's move on to the PCB site, and again we saw very high variability between PCB concentrations reported for individual samples. This is looking at the intrust sample variability for grid point 24. Lowest concentration reported for the sample, 810 milligrams per kilogram. Highest concentration, almost an order of magnitude greater, 5,700 milligrams per kilogram. Now, at this particular site, the average ratio between the minimum and maximum concentration of PCBs reported within an individual sample was well over an order of magnitude. And the maximum to minimum ratio we saw within an individual sample was actually over 2 orders of magnitude. So again, this is all just random aliquots of soil tested from individual samples, and start thinking about the implications. This was the intrust sample variability. So this is an example of the inter-sample variability at the PCB site, again for grid point 24. So just ignoring the concentration in the red for a moment, looking strictly at the co-located samples in black, the lowest concentration of PCBs I reported for one of the samples was 4.9 milligrams per kilogram. Highest concentration just a foot away, 91 milligrams per kilogram. Again, the concentrations are completely random, not indicative of larger scale trends. Let's look back at the sample collected at the same grid point and tested individually. Look at intra-sample variability. The mean concentration of PCBs in that sample was 2,400 milligrams per kilogram. So there's a true hot spot, and it is the size of a spot, and it's surrounded by samples with significantly lower concentrations of PCBs. This just goes further to highlight the random variability you can see in discrete soil samples at any given point. The average maximum to minimum variability between co-located samples was over an order of magnitude. The maximum to minimum ratio between co-located samples at grid point in this particular point was almost 500-fold. So again, start thinking about the implications of this. So what's causing this high variability at the PCB sites? And we see this at a lot of PCB sites that we investigate when we were using discrete soil samples in the past. So in this case, we took a sample of the soil we knew had high concentrations of PCBs reported for some of the subsamples, looked at under a microscope. And what you can see, starting off at the bottom right-hand corner, we found these small nuggets of soil easily crumble. There was a lot of lithic fragments in the soil too, but some of these nuggets of soil, if you pushed on, they would crumble really quickly. So we knew there weren't rock fragments. And look at that in the middle sample. They're about 2 or 3 millimeters across in length, about 1 millimeter across, again easily broken. And then zoom in even further, and these things look like small eggs or something. And you'll see there's a very distinct outer rim on these small nuggets of soil. And what we think these are, we're almost positive they are relic drops of PCB infused oil that sank into the soil and then later on degraded to form what we were calling PCB infused tar balls. So how are these created? This is a chemist who likes to cook showed me how to make these type of nuggets in soil, and in this case he said get some dry flour and just pour olive oil on it. And what happens when you pour olive oil or any oil on a dry material like a soil, then first the oil will quickly retract into droplets, and then over a few minutes these droplets will slowly sink into the soil, as you see on the bottom. Look at the bottom right hand figure. One very distinct thing about these droplets after they've sunk into the soil is you'll see a distinct rim around the edge of the droplets. The same thing that we saw the PCB, the hypothesized PCB nuggets in soil. Then in the upper right hand corner, if you let the oil sink into the flour wait a few minutes and then sieve it, then you'll find all these small olive oil infused nuggets in the flour. So we're pretty confident this is what's happening at some of these PCB sites when PCB infused oil is dumped on dry soil. So here's a summary of our field investigation then. We're at the study site A for arsenic. On average, when you combine the intra-sample variability and inter-sample variability around any given point, we see about a twofold variability of concentrations around any given grid point. So if you collect a discrete soil sample at this site, and then move over a foot or two and collect another sample, that sample might be 2 times higher or actually even 2 times lower. That's low variability compared to the other sites we looked at, although that could obviously cause some problems as part of a site investigation. At the lead contaminated site, we saw an estimated overall variability around individual grid points of 7.5 times, so much higher than we saw at the arsenic contaminated site. And then at the PCB site, on average, we saw estimated variability of PCBs and discrete samples around any given grid point of about 39-fold. Now, these are just initial estimates. We only tested a very small amount of the soil around any one of the grid points. If we collect more samples at each grid point, I'm sure we'd find more and more variability. So here's the bottom line then. Discrete samples are just simply too small to overcome and capture random small-scale variability of contaminants in soil. Now, the farmers and miners have known about this for decades. They started to realize this problem back in the 1950s and 60s and quickly moved away from discrete samples. In the environmental industry, it's only started really in the 90s with the Army Corps of Engineers, and in the early 2000s with states such as Hawaii. It's just now catching on. The reason it's taken longer to catch on in the environmental industry is there's no test of the reliability of your data like there is, say, in a mining or mineral exploration investigation, where you quickly find out if your data for gold or something in the soil or in the rocks was erroneous when you set up an operation to extract that gold from the rocks, and you find out there's actually nothing there, or maybe there's a lot more there than you thought in the first place. So in the end, the bottom lines are that the laboratory data for discrete samples are not reliably representative of the discrete sample submitted, and the discrete sample is not reliably representative of the immediate area where it was collected. So let's put it in terms of food. As what we thought in the 1980s, I like to think of it as the contaminated soil or contaminants in soil was like a bowl of Cheerios. You could pick any individual grain or any individual piece, and you're going to get the same concentration no matter how big that piece is or where you collected it. So the size, the mass of the soil tested, and where that sample came from isn't really important if you were testing what you thought was a known spill area. The mass of the soil tested in environmental investigations is instead driven totally by what the laboratory needs. What we know now in the 2010s is that contaminated soil is more like a bowl of Fruit Loops. So contaminant concentrations can vary very widely and randomly within a small mass of soil, within a small area of soil. So in this case, what we now know is that the mass and location of the sample collected and how it's collected are indeed very important if you want to collect a representative sample. And this is essentially the basis of multi-increment sampling and sampling theory. So think about the implications. This is another quote from my favorite movie, The Matrix. You take the red pill, you stay in Wonderland, and find out how deep the rabbit hole goes. We're all here listening to this, so we've all decided to take the red pill. And one thing I semi-joke about is that anytime anyone who's spent their career testing discrete soil samples and making decisions based on discrete soil sample data, we all go through the same 5 stages of grief. Our office definitely did. Through denial, anger, bargaining, depression, and acceptance. So hopefully you'll get through that faster than we did. Hawaii actually spent several years implementing their multi-increment decision investigation guidance as we looked at this in more and more detail. But since 2004, 2005, since we implemented the program, I think over 15,000 multi-increment samples have been collected and tested in Hawaii now. And we're a small state, and that's the basis for decision making at essentially every site that we work on now. So it took a while, but now we're using it at every site. So let's look at the implications real quickly. Here's an example that's used in ITRC's incremental sampling methodology guidance, essentially the same thing as multi-increment sampling. Why DUs and ISM are important. This was an example site from Hawaii known to be contaminated with PCBs. A lot of discrete samples have been collected at the site, and we thought we knew where the PCB contamination was. But looking back now, and once we started looking into the multi-increment sampling and understanding the variability with discrete samples, we knew that false negatives were unavoidable as you move away from the heavily contaminated area. You're going to hit a small pocket of soil that's clean in an area that is otherwise contaminated, or you could. So we didn't know, so we went back to the same site and did a more detailed multi-increment decision and investigation. Here's what we found: a lot more contamination at the site. So the discrete sample data significantly underestimated the extent of contamination. Now, one of the ironies here is that the multi-increment sample data found a lot more contamination, and not surprisingly, it found higher concentrations of contamination because you're collecting much bigger samples from many more points, so you're starting to pull some of these nuggets into the samples that actually get analyzed. So in the discrete sample investigation, the highest concentration of PCBs found in any discrete sample was 49 ppm. And once we went back and collected multi-increment samples, we started finding PCB concentrations within our decision units in the hundreds of ppm. So quite ironically, this site got referred to TSCA for co-oversight with the EPA. And although the scientists with TSCA, they understand the problems with discrete samples, some of the enforcement people still aren't quite convinced of the problems with discrete samples, and they're currently requiring that we go back to discrete soil sampling at this site and collect almost 1,000 discrete soil samples. This is at a 1.5 acre site, which is it's pretty absurd. But one thing it's really helping us do is force a more intense look at problems with discrete samples. And this is actually one of the impetuses for us to do the field study in the beginning. So hopefully we're going to get this problem straightened out before they start additional investigation at this site later on this fall. I'll keep you posted. So another classic pattern that you see related to small-scale random heterogeneity is the seemingly isolated hot spots and cold spots. This is another PCB site where hundreds of discrete soil samples were collected and tested for PCBs. Now in this case, the people collecting these understood the problems with discrete soil samples, but they were using a tight grid of discrete soil sample data to help identify large-scale patterns of PCB contamination across the site. But this still gives you a great classic sign of random small-scale heterogeneity when you see these isolated hot spots and cold spots. If you shifted the grid over 5 feet or even a few inches or whatever, then you'd see similar patterns. You'd see more PCBs on the left-hand side of this site than on the other parts of the site, but the hot spots and the cold spots would be in different places. And that's just an example of the variability of the site. So resampling would show similar spots and patterns, but in different locations, small-scale patterns. The large-scale patterns we would anticipate would be similar. So this is the more realistic resolution of PCB data, discrete sample data, and that's the key thing with discrete sample data. You need to think in terms of resolution, and what kind of resolution is actually reliable based on the data. So it's not those individual spots. It's something like this. We can say that most of the property on the left-hand, most of the PCBs are on the left-hand side of the property, and there are these apparent smaller areas of PCB contaminated soil in the right-hand area of the property. So you can use your PCB discrete sample data to go back in and do a more focused DU-MIS investigation to get more reliable data on the concentrations of PCBs in decision units and estimate risk. Here's another great example. This is arsenic in U.S. surface soil. Is a big investigation carried out by the U.S. Geological Survey, published in 2014, where they collected over 4,000 1 square meter samples across the U.S. These samples were ground and then subsampled and tested, so the data for any individual point we'd consider highly reliable. But real quickly here, you see the same thing. The large-scale patterns you see on this map are real, and if you look at it in more detail, they actually reflect the geology and soil types in these different areas. But if you zoom in, you see lots of small hot spots. They stand out more, but you also see lots of small cold spots. So these are completely artificial, and they just reflect small-scale random variability within those areas of arsenic concentrations. Now, if you read the fine print of the USGS document for this investigation, they state this exact same thing, that large-scale patterns are real, small-scale patterns based on one or even a small cluster of discrete soil samples can't be considered accurate and could be artificial. So here's actually an example artificial 2,400 square kilometer arsenic hotspot in North Carolina. It's based on a single 1 square meter discrete soil sample. So how reliable do you think that is? Well, it's not. I happen to be very familiar with this area. It's where I did my undergraduate degree in geology. So this area is characterized by very heterogeneous metamorphic rocks. And within these metamorphic rocks, you'll find these very narrow, sometimes just a few feet wide, mineralized zones. This is where you could very easily find higher concentrations of arsenic. So that's probably what happened with this one sample that created a 2,400 square kilometer hotspot. It just happened to be located on one of these narrow mineralized zones. If you shifted all these sample points over a few feet, you'd probably see a very similar pattern, and you'd see hot spots and cold spots, but they'd be in different areas. So that's a key thing to keep in mind with discrete sample data. And again, we use tight grids of discrete sample data sometimes to help us locate larger scale contaminant patterns at sites that we don't have much information on, but you have to be very careful about over-interpreting the data on individual points, especially when you're using computer-generated isoconcentration maps. They can be highly misleading for small areas. Here's a more realistic resolution of the USGS arsenic data. We tried to get them to include this in their report, but they wouldn't do it. They just included the fine print. In this case, we've filtered out the small-scale heterogeneity within the larger scale patterns, and this is just something I put together very quickly, just as an example. But it gives a much more realistic idea of arsenic concentrations in soil across the U.S. at large-scale patterns. Now, there's a myth that statistics can fix the problem with any set of discrete soil sample data. Let's look back at the lead-contaminated site and think about mean concentrations of lead in that area from a risk assessment side. So if we just took the lowest concentration of lead reported at each one of those 24 grid points, then the mean concentration comes out to 131 milligrams per kilogram. RSD is 58%. The 95th percent UCL 151 milligrams per kilogram. So it's below our action level. If we took the median data points, discrete sample data points for each one of the grid cells, we come up with a mean of 262 milligrams per kilogram, RSD of 53%. It's kind of high. It tells you there's a lot of variability. But then a 95th percent UCL, 325 milligrams per kilogram. So suddenly you're over Hawaii's action level for lead in soil, but you're still under the US EPA's current action level of 400 ppm lead in soil for residential use. Now what if we took the highest concentration of lead reported at any individual grid point? Then we come up with a mean concentration of 452 milligrams per kilogram. RSD still a little high, 64%. 95th percent UCL now is 559 milligrams per kilogram. So there, even just looking at the UCLs, depending on which random set of discrete samples you tested at the site, they could fall between 157 ppm and 559 ppm. So which one of these is real? Well, you have no idea, because you have no idea which set of data is actually representative of the site. So actually, all these sites, we also collected multi-increment sample data. So we considered each of the study areas individual decision unit. This is the lead site. We collected triplicate 60 increment multi-increment samples from this site. Each of them weighed 1 to 2 kilograms. So if you're not familiar with multi-increment samples yet, we collected small masses of soil, say 20 to 50 grams from 60 different points within that area, combined them into one large sample. Then the laboratory took this sample, they air dried it, they sieved it, and then they very carefully subsampled it and tested a minimum 10 grams mass, which is required by sampling theory instead of 1 gram, to come up with the concentration of lead in each sample. So you can see the results, the triplicate samples in the upper right, and very good correlation, and very good reproducibility, ranging from 240 ppm to 350 ppm. RSD, relative standard deviation, 20%. If it's below 35%, then that's really good. The mean in this case comes out to 287 ppm, so it's above our action level. 95th percent UCL, if you were going to use that, 345 milligrams per kilogram. Now in our guidance, our updated guidance should be posted this summer. If the RSD is below 35%, we just go with the straight mean. And for decision units that don't have replicate samples, we just go with the straight data. Once the RSD gets over 50%, then we require the use of 95th percent UCL to estimate mean concentration for individual DUs, and it may even push to get additional data for the site. So what's some other risk problems or other problems associated with risk assessments using discrete sample data? And that's one thing that's always bothered people who collect the samples, including me. And I'm both a geologist and I do a lot of risk assessment work also, is tossing out the outliers. So that's a key mistake that we've made for the last 20 years, is don't throw out the outliers. If you're reading the quote in the bottom left-hand corner, this is from the EPA 1989 guidance we mentioned before, methods for evaluating the attainment of cleanup standards. All data not known to be in error should be considered valid. High concentrations are of particular concern for their potential health and environmental impact. So this same document, at that time they thought discrete samples were representative of areas, which they turned out not to be, which we now know, but they hit the nail on the head when they said you can't toss out data just because it doesn't fit with the other. So statisticians often get stuck with uninterpretable discrete sample data sets. So the exclusion of outliers from data sets distorts the estimation of the mean in the risk assessment, but it's not the statistical method, it's not the statistician, it's the sampling method. It's the people collecting the samples in the field not collecting proper sample data for the statisticians to look at. And my background is actually in geology and mineral exploration, and I can assure you that you'd get fired if you deleted or overinterpreted data for discrete gold veins in an ore body. Like give an example in the bottom right-hand corner. So this has been a problem in the past, decades ago, in mining. If you only collected a sample that had concentrated veins of gold in it and used that to set up a mining operation, you could get in a lot of trouble. Or if you happen to collect a sample, a very tiny piece of rock outside of the gold mineralized areas, and assume that was representative of an area, then you could really miss out on some large gold deposits. So another problem with risk assessments is hang up on acute risk, and especially the myth of maximum contaminant concentrations in soil. And even from the geologist side or the field investigation side, there's always been this drive to find the maximum concentration of a contaminant in soil. It has nothing to do with risk. If you look at the bottom bullet down there, for one thing, it's not possible to test every 10-gram mass of soil that might be considered to pose an acute risk. If a child happened to eat a spoonful of soil, there also are no toxicity factors in most cases to develop screening levels for acute toxicity. And the assumption is it's valid, proven valid over time, is if you address chronic risk or long-term exposure to contaminants in soil, then you're also going to be addressing acute risk. If you're concerned about acute risk at a site for some reason, then the only thing you can do is remove the soil or cap it. There's no way you can confirm every gram of soil meets some hypothetical screening level. But looking at the concentration of the attempts to find the maximum concentration of contaminants in soil, the concentration of a contaminant in soil varies with the mass of soil tested. So back to this slide, and looking at the lower left-hand corner, if we tested all the soil within that figure, then we get a concentration of PCBs probably in the low ppm range. You see that one nugget of PCB-infused soil we have outlined. What if you zoomed in and were able to actually test one of these nuggets of soil? You'd probably find PCBs in the thousands of ppm range, testing a much smaller mass. You're not diluting it with the rest of the soil. Let's zoom in, and what if we tested the matrix in one of these nuggets? So these nuggets are degraded PCB-infused oil mixed with silt and other fine material. What if you could just test the oil itself? Then you'd probably find PCB concentrations in the hundreds of thousands of ppm. And in theory, if you had some type of equipment like a microprobe, you could zoom in and test the tar itself and test individual points within it down to the molecular scale. Then at some point you're going to find PCB concentrations of 1 million parts per million, or 100%. So the question always comes up, what's the maximum concentration of contaminant in soil? That's actually very easy to answer. It's always 0% if it's not there, or it's 100% if it is there. So one thing we've been really distracted on the last 20 years was looking for maximum concentrations, when in reality we already had the answer. It's 100% or 0%. And it really has no basis in risk to begin with. So in quick summary, discrete soil sampling methods can identify the core of heavy contamination. That's what we've seen when we've gone back and tested sites that hadn't been completed as far as cleanup goes. But so in this case, any small mass of soil is going to exceed the screening level. You can't miss in those cases, but you very quickly will start to hit false negatives as you move out from heavier contamination, and you'll prematurely terminate the investigation. That's really unavoidable, to hit false negatives. Once you start to hit areas of soil where tiny masses, the concentration can be both above and below screening levels. Now also, discrete soil sample data create a lot of confusion over these artificial hotspots based on one or two samples that are simply reflecting heterogeneity in the soil. And removing these, trying to excavate individual spots around discrete samples, is really a fruitless effort, because you're not necessarily reducing the risk for the soil in general. So the representativeness of a discrete sample data set, also using risk assessments, is never directly testable unless you collect replicate sets of data. So you can have 20 discrete samples for a site, calculate means and UCLs and such using a risk assessment, but you really have no idea if those data are representative of that area where the samples were collected. And we demonstrate over and over in sites we've looked at that in many cases, even 30 increment samples collected for say a target exposure area, you can't get reproducible data. So 30 samples wouldn't be enough to get representative data. PCB sites in general, we've increased the default number of points you need to test within any given area to 75. That's really the point where you can start to get reproducible data in some of these really heterogeneous sites. Also, problems we talked about was deletion of outliers in risk assessments, which is it's completely erroneous and it distorts the estimation of the true mean. And there, you're just trying to force the data to fit some statistical test instead of trying to collect a samples that are actually representative of the site. So the use of discrete soil sampling methods, although again can be very useful for initial screening of sites, especially when you can use field screening and identify large-scale patterns. But after that, discrete soil sample data can be highly efficient at best, trying to map out the extended contamination, and highly misleading at worst. And again, this is nothing new to people who've been doing this, I think, for decades. We just didn't have a good solution until we started looking in more detail at sampling theory. So the solution is actually really simple. I'm not going to spend a lot of time on this. This is in our Decision Unit Multi-Increment Sample Guidance. So that Dr. Seuss, a great quote from some of his books, sometimes the questions are complicated and the answers are easy. It is complicated to understand problems with discrete samples if you've been ingrained in that, like I was and a lot of my friends the first decade or so of your career. But in order to collect a representative sample, there's just a few simple steps. First, step one is you need to designate well thought out decision units for characterization. These can focus on suspect spill areas or exposure areas that might be used in a risk assessment. So you go and draw a line around these areas you're concerned about. And then from these areas you can collect a single sample, but it's going to be a very big sample, 1 to 2 kilograms. This is driven by sampling theory, from multiple points across the DU. That's why we use the term multi-increment sample. Instead of a single sample trying to represent a spill area or even 2 or 3 samples, you need to collect a sample from lots of points, at least 30. If you're looking at PCBs and lead or something, you're looking at 50 to 75 points before you can get reproducible representative data. So once you get this big sample, you send it to the laboratory. It needs to be properly processed. They can't just open the bag and collect a pinch of soil and test it. They have to dry the sample, sieve it, and then subsample it very carefully, mimicking what you did in the field, collecting an aliquot to test from at least 30 points, and then testing a minimum 10 grams to get representative data. So in this case now, the data represents the sample you sent in, and the sample represents the area that you collected it from. This significantly improves data reliability, and ultimately it expedites completion of projects, even though you may spend more time up front. So here's some of the references and training courses. We'll be giving workshops later on this year on updates to our multi-increment decision unit sampling guidance. A great place to start off is ITRC's Incremental Sampling Methodology Guidance. Several people from Hawaii were involved in this. It gives a good introduction to incremental sampling. Not a lot of information on how to implement it in the field, because at the time the group was working on this in 2010, very few people actually had experience. If you want to learn the details of sampling theory, then one of the best classes you can take is Chuck Ramsey's 4-day detailed introduction to sampling theory and multi-increment sample site investigations. So he looks at not only soil but water, food, anything, just how to incorporate sampling theory into your investigations. If you really want to get into the nitty-gritty details, Francis Pittard, who is one of the original developers of sampling theory, teaches a longer class on advanced statistical sampling concepts. He focuses on optimization of sampling protocols for mining exploration, where they really have to be very careful about their data and have highly reliable data. Then our guidance we publish here in Hawaii. We're about to publish updates sometime this summer. 3 different sections. We look at sampling theory and systematic planning, designating DUs in Section 3. Section 4, DU characterization, where we obviously emphasize multi-increment sampling once you've designated areas for characterization. And then Section 5, we get more into details of field implementation down to the type of tools that work in different types of soil. And again, we'll be giving workshops on updates to this later on this year. So that obviously was much longer than the presentation I gave at Battelle, but wanted to get some other details in there. The key thing to remember is that multi-increment sampling or incremental sampling, it wasn't developed as an alternative to discrete samples. So it's not just another tool in the toolbox, it's an entirely new and improved set of tools. And it was developed to specifically address the problems that we were having with discrete samples. So it's discrete. I don't know of any cases where I would only use discrete samples to make calls at a site, just knowing their unreliability. So the wrong question is, when are DU, IS, or MIS methods applicable? The right question is, knowing what we know now, when are discrete sample methods acceptable? Thanks.